Hello and welcome to the Pauli Matrices and the Algebra of Quantum Mechanics. My name is Dr. Jacob Hudis. This is a short presentation on the Pauli Matrices. It's a follow-up to Lesson 2b. Today, I will discuss the Pauli Matrices more slowly and thoroughly. And here's an outline of the adventure ahead. It's going to be an exciting one. I'll introduce the Pauli Matrices. I'll then explain that the Pauli matrices form a basis for the vector space of 2 by 2 Hermitian traceless matrices. Next, I'll list the properties of the Pauli matrices. Then I'll move on to introducing the normalized eigenvectors of the three Pauli matrices. And then finally, there will be a detailed example where I demonstrate that the eigenvectors of the Pauli matrices form a complementary basis set. This is the mathematics of the uncertainty principle. On this slide, I introduce the three Pauli matrices and their associated eigenvectors. Here are the three Pauli matrices, sigma x, sigma y, sigma z. Sometimes this is sigma 1, sigma 2, sigma 3. These are the eigenvectors for sigma x plus or minus x. Here are the two eigenvectors for sigma y, and these are the two eigenvectors for sigma z. The Pauli matrices are the basis of matrices for all 2 by 2 traceless Hermitian matrices. The Pauli matrices have eigenvectors that span the space C2. There are two vector spaces. One of them is for matrices, and the other one is for conventional vectors. Here's the Austrian physicist, Wolfgang Pauli, next to me. These are the three Pauli matrices, and they form a vector space of 2 by 2 traceless Hermitian matrices. This vector space has a name. It's actually called a Lie algebra. Any 2 by 2 traceless Hermitian matrix can be broken up into a linear combination of the basis matrices. Here's an example of this. Here's a traceless 2 by 2 Hermitian matrix, and as you can see, this matrix can be decomposed into 2 times sigma x plus 3 times sigma y plus sigma z. On this slide, I'm going to list the properties of the Pauli matrices. The square of the Pauli matrices is equal to the identity. For example, sigma x squared is equal to the identity matrix, sigma y squared, that's also equal to the identity matrix, and sigma z squared is equal to the identity matrix as well. All of the Pauli matrices have a determinant of -1. All of the Pauli matrices have a trace of 0, and they all have eigenvalues of plus or minus 1. They're unitary as well as Hermitian. Because they're unitary, they have to have unit eigenvalues. The Pauli matrices satisfy this commutation relation. This is what makes them a Lie algebra. These are the commutation relations, and so for example, the commutation of sigma x, sigma y equals 2i sigma z, and that's done. That calculation is performed down here. Sigma x times sigma y minus sigma y times sigma x is equal to 2i times sigma z. On this slide, I'm going to introduce the three sets of normalized Pauli eigenvectors. These are important vectors that you should know. There's the z basis. The z basis has two vectors. Plus z is 1, 0, and minus z is 0, 1. Then we have the x basis, which is 1 over root 2, 1, 1, and 1 over root 2, 1 minus 1. And finally, there's the y basis, which is 1 over root 2, 1i, and 1 over root 2, 1 minus I. I get keloids, so I can't get tattoos, but if I was going to get a tattoo, these normalized Pauli eigenvectors would be a nice choice. On this slide, I'm going to talk about an important property of complex numbers. Complex numbers can be represented in two ways, as a magnitude and a phase, or as a real and imaginary part. There are two equivalent ways to write any complex number. C is a complex number, and it can be written as a real part and an imaginary part. You can plot the complex number C on the complex plane. This is the imaginary axis and the real axis, and C is either a vector or a point at location 3, 4. Now, C can also be written as a magnitude and a phase. The magnitude of C is equal to the amplitude, which is the square root of x squared plus y squared. In this case, it's the square root of 3 squared plus 4 squared, so it has a magnitude of 5. The angle is the inverse tangent of y over x. In this case, y is 4 and x is 3, and so it has an angle of 53.13 degrees. This is the complex number written in the real imaginary form, and this is the same equivalent complex number written in the magnitude phase form. Both of these complex numbers are the same. They're identical. Are you in need of a great physics tutor? Dr. Hudis can help. Whether you're preparing for a high school test, AP test, or college exam, let me help you ace it. Are you an eager high school student aiming to get ahead and prepare for college-level physics? Or maybe you're a college student and you want to learn even more advanced physics? Dr. Hudis can help. Visit acephysics.org and schedule a lesson today. The eigenvectors of the three Pauli matrices form three distinct bases for the two-dimensional complex space C2. The sigma x bases, sigma y bases, and sigma z bases are three complementary bases that span C2, the complex space of two-component vectors. Any vector in C2 can be written in the z basis, the x basis, or the y basis. If I take some vector v, it can be written as a linear combination of plus z and minus z, where a is a complex number and b is a complex number. The same vector v can be written as a linear combination of plus and minus x with two different complex numbers, and you can write it in the y basis as well. On the next slide, I'll do an example. Any vector in C2 can be written in the z basis, the x basis, or the y basis, and I'm going to do an example on this slide. Here's a vector in space C2. It has two complex numbers. One complex number is 2 plus 0.5i, and the other complex number is 1 minus i. If I write this vector v in the z basis, it's equal to this complex number times plus z plus this complex number times minus z. I can also write the vector v, the same exact vector, but now it's in the x basis. So in the x basis, v is equal to this complex number times plus x plus this complex number times minus x. I've written plus x and minus x above the equation. If you were to plug plus x and minus x in, which I recommend you do, and do the multiplication and the addition, you'll find that this has to equal the vector v. And finally, I can write the vector v in the y basis, where v is equal to this complex number times plus y plus this complex number times minus y. On this slide, I want to discuss complementary bases in quantum mechanics and linear algebra. The two bases are considered complementary if a vector from basis A can be constructed by an equally weighted sum of all vectors from basis B. There's the primed and the unprimed bases, and they're rotated at 45 degrees relative. In the unprimed basis, A was all along one direction, the z direction. In the primed basis, A had an equal amount in every basis direction. That's what it means to be a complementary basis. Now I move on to an example where I demonstrate that the eigenvectors of the Pauli matrices form three complementary bases. These two vectors, plus x and minus x, are both vectors in the space C2, and therefore they can be written in the z basis. They can be written in any basis that spans C2. What I want to do is I want to write plus x in the z basis, and I want to write minus x in the z basis, and this is to demonstrate the complementarity. Plus x is equal to 1 over root 2 times plus z plus 1 over root 2 times minus z. In quantum mechanics, we use complex numbers, so we write it as a magnitude and a phase. The magnitude is 1 over root 2 and the phase is 0. Plus x is e to the I 0 over root 2 times plus z plus e to the I 0 over root 2 times minus z. I can also write minus x in the z basis, and minus x is 1 over root 2 times plus z minus 1 over root 2 times minus z. And we write this as e to the I 0 times 1 over root 2 times plus z plus e to the I pi times 1 over root 2 times minus z. E to the I pi is minus 1. Recall the phase of the complex number has nothing to do with the magnitude. This example shows that plus x is made up of an equal amount of plus z and minus z, namely 1 over root 2, and minus x is made up of an equal amount of plus z and minus z. On this slide, I want to take the same two vectors, plus x and minus x, but now I want to write them in the y basis. I'm going to decompose plus x into some amount of plus y and minus y. I'm going to decompose minus x into some amount of plus y and minus y, because these are a basis that spans the space C2, and both of these vectors are vectors in C2. Plus x is equal to the complex number 1 over root 2 times the phase, e to the minus I pi over 4 times plus y, plus the complex number 1 over root 2 e to the I plus pi over 4 times minus y. If I replace plus y with the vector that it is, plus y, and I replace minus y with the corresponding vector that it is. Next, I write the complex number in terms of a real and an imaginary part. And then here you have an equation, and when you do the math, you see that it does in fact equal to 1 over root 2, 1, 1, which is the vector plus x. Recall the phase has nothing to do with the magnitude. They all have a magnitude of 1 over root 2. That means plus x is equal to an equal amount of plus y and minus x is made up of an equal amount of plus y and minus y. And here's a summary of the example. The Pauli matrices exhibit the property of maximum non-commutivity and possess eigenvectors that demonstrate complementarity. Plus y is equal to an equal amount of plus x and minus y is also equal to an equal amount of plus x and minus x. The magnitudes of the complex numbers are the same. The phases aren't, but the magnitudes are. You should study this slide carefully and make sure you understand it. The point is that all the complex numbers have the same magnitude. Every complex number on this slide has the same magnitude of 1 over root 2, and that's because each vector can be decomposed into an equal amount of the basis vectors. This is the mathematics that underlies the uncertainty principle in quantum mechanics. The picture on this slide is helpful to visualize complementary bases when you're dealing with the Pauli matrices. Make sure you understand this picture because this is helpful in understanding this material. This is the negative x-axis, and this is the positive x-axis. This is the plus y-axis, and this is the negative y-axis. So for example, if you're in the negative x direction, that means you're an equal amount of plus y and minus y. If you're in the positive x direction, you're an equal amount of negative y and plus y. All right, finally, here's a summary slide. These are the three Pauli matrices. These matrices form a vector space of 2 by 2 traceless Hermitian matrices. The eigenvectors of the Pauli matrices form a vector space of vectors in C2, and there are 3 bases for that vector space. You have plus or minus x, plus or minus y, and plus or minus z. I discussed in lecture 2a that the exponential of the Pauli matrices produce unitary matrices, unitary operators, and these operators work on the space C2, and these are the generators of SU2. The exponential of negative I times sigma x theta is this important matrix. The exponential of negative I times sigma y theta is this important matrix, and the exponential of negative I times sigma z times theta is this important matrix, and these are the generators of SU2. acephysics.org. Math and Physics Tutoring with Dr. H. acephysics.org. Math and Physics Tutoring with Dr. Hudis.